This is lab 2, which is lines of charge. So to introduce it, this purpose of the lab is to create a computational model that shows the electric force of two charged tapes, as well as estimating the amount of charge needed to float one tape above the other while distributing the charge evenly across the tape, aka not a point charge. The fundamental physical principles is Coulomb's law, which is pictured below, as well as Newton's second law, force equals mass times acceleration, and superposition, as the charge is now evenly distributed. So the main physics ideas is we are now considering the tape has a distributed charge, so we will be using superposition to essentially create a long line of point charges, which is also the model that is used here. So results overview. The results from experimental data from lab 1, which we treated as point charges, had a charge of 1.27 times 10 to the negative 8th, and we showed this was very inaccurate using my model, as the force of gravity was much larger than the force of the electric force. So using superposition provided much more accuracy, as the charge was 2.6 times 10 to the negative 8th coulombs, and as you can see, the gravitational and electric force outputted almost equally. So here is the experiment, just going over lab 1. Negligible air resistance, each piece of tape has the same charge, and the charge is evenly distributed throughout the tape are our assumptions. The system is tape B, the surroundings is tape A. The initial conditions is a piece of tape on the desk was stuck with another piece of tape and ripped off quickly in order to charge it, and then there is the actual image of it floating. So here are the details. Again, I placed tape on top of the other to charge it, and then tape B was placed above tape A until it began to float, and the distance was measured with a ruler. So there's a photo of it on my desk. So here is the data. I have the length, the width, the distance in between them, the mass of the tape, and the area. Here are the calculations. I set the gravitational force equal to the electric in order to get the charge. This is just a recap of lab 1. So here is the actual coding. I inputted the mass and the net charge, as well as the K value and the gravitational value. Here is the definition of an electric field. So we created a function for it using the R vector, magnitude, and the unit vector. And you can see E down there is the actual calculation. And then over here, this was the function that created a line of charge, which we did not alter. Over here, you can see the top tape, which was altered to have the distance as the Y portion, and then 0.2 was already close enough to my length. And then here is the scaling of those vectors, so your gravitational scale and your electric scale should be the same. And then down there was an edit adding the electric field at the top times the electric scale, as well as an edit showing the calculation of the electric force at the top due to the bottom. Over here, this is the actual creation of the arrows, and the main edit here was that the gravitational force arrow has a negative mg as the Y value, as well as multiplying by the top at the very beginning. So going back, here is the output of using lab 1 data. As you can see, the electric force is much smaller than the gravitational force, meaning it's not accurate. But how do we increase this accuracy? So using the equation for an electric field that we derived in class, which is pictured at the very top, I then know that force is charge times the electric field, so that Q turns into a Q squared. And we can actually equate that with the gravitational force, because the electric and gravitational should be equal, in order to get an equation where we isolate Q. So as you can see, Q is isolated there. It has mg times xo squared plus L over 2 squared, and then that parentheses is in a square root divided by your K value, and then the square root of everything. Because again, we isolated the electric force equal to the gravitational force in order to find this Q. So plugging all of that in, I then got 2.599 times 10 to the negative 8th coulombs as the new charge using superposition. So here it is with the edit. So now that Q is equal to the new charge that I calculated. And here is the new output. So as you can see, the magnitude of the electric force and the magnitude of the gravitational force are extremely close to equal. So to discuss them, the similarities and differences, the code does not assume the tapes are point charges like lab 1 did, and it does still take into account the gravitational force as lab 1 did. Possible sources of error, the charge maybe isn't evenly distributed, and maybe the two tapes do not have equal charges. What if we had modeled them as a single point charge like the previous lab? We compared this earlier. The point model charge is much more inaccurate and has a much lower value. Why did these differ? The second one is closer to the real value, as superposition takes into account the charges going across the entire tape, whereas the tape cannot be accurately modeled as a point charge. So our conclusions: superposition is much more accurate than describing it as a point charge, but there is still a small loss of accuracy.